when we've been looking for our half reactions, we've always been looking at those numbers on the side. Today we're going to use those. Those are cell potentials. Yes, sir.
Can you go over to question 6 then afterwards?
Yeah.
From the work?
Yeah.
Yes, sir.
Yeah.
Yeah.
Okay. So electric potential difference is the measure of the electrons flowing from anode to cathode. The higher the potential, the greater the electrons will flow, which means that we're going to have a greater reaction, like the transfer of the anode breaking down to the cathode building up. It will happen more readily. Okay. Electric potential difference is measured in volts, and so it gets called a number of things. It can get called the voltage, it can get called the cell potential, it can get called the electrical potential, it can be potential difference. Usually you see the word potential in there. Okay, don't forget that the symbol above the salt bridge is usually a V or some kind of indication that there's a current, because it generates, it converts chemical energy into electrical energy. So what happened was somebody had a lot of time on their hand and they did experiments and they calculated out, they measured out those electric potentials that we see listed on the side in the data booklet. Those are standard. Those always have that value. So somebody did a lot of work a long time ago and figured that out, and people were able to replicate the test. That's key in science, is that not just that Jaden can do the test, but that Reese can do it and come up with the same numbers. Okay, so that it can be replicated. Find that on the right-hand side of page 7. And so a voltaic cell requires 2 reactions. It takes the oxidation half reaction and it takes the reduction half reaction. And so standard reduction potentials are recorded against hydrogen. Hydrogen is the standard. And if you look, the reaction for hydrogen has what cell potential on page 7?
0.
0. Okay, so everything that's in that book is referenced against hydrogen. So if we look at it here, and cell potential is shown like this, E with the 0. So this is the standard reduction potential. Okay? Because this here is the reduction half reaction. So hydrogen half cell is assigned a voltage of 0. So it is considered to be the reference cell or the half cell, half reaction. All other standard reduction potentials are referenced to hydrogen. Okay? And so you use those to calculate the cell potential. Any voltaic cell can have it calculated out by taking the potential voltage of the cathode and subtracting it from the potential voltage of the anode. Okay? You can't change the values. Don't change the sign or multiply by a coefficient. These values are the way they are. So unlike when we're balancing half reactions and we multiply everything through, even if you have to multiply it by 1 by 6 and 1 by 4, you don't multiply the cell potential by that value. Or like when we were looking at where we have to flip the sign, the energy. When we have to flip the energy, when we make the reverse reaction, you don't take your negative 1.77 and change it into a positive if you had to go forwards or backwards. Okay? That never changes. So you have to be able to identify the oxidation half reaction, right? And we did that. We were getting really good at this. And you have to be able to identify the reduction half reaction. So, oxidation occurs at the anode and reduction occurs at the cathode. That never changes for a voltaic cell. Okay, and the trick that I use is oxidation occurs at the anode. That's the only one that works that way, but that's a trick that I learned to remember that. Okay? So the anode is always the strongest reducing agent. Okay? It's the oxidation half reaction. And it's the most negative reduction potential. So then that means that the cathode, this must be the strongest.
Oxidizing agent.
Yeah. It's the which reaction?
Reduction.
Reduction. As I write it out. Okay, and it's also going to then be the most positive. And yes, the word reduction does belong there. Okay. So when you have an oxidation half reaction, that's happening at the anode. It's the strongest reducing agent, which means that we're looking at the bottom right-hand side of that chart. Whereas the cathode is the strongest oxidizing agent, so we're looking at the top left-hand part of that chart. Okay? Makes sense so far? Yeah, sort of, kind of.
Smartboard's a bit off.
Smartboard's off. So it says calculate the standard electric potential for a voltaic cell that has copper solid and zinc solid as electrode. So if we have copper solid, chances are we're going to have a copper species. And if we have zinc as a solid, we're going to have zinc as a species. Zinc ions. Okay? So now that we've identified those, we go to our chart and we determine which do we see where. Strongest oxidizing versus strongest reducing agent. So what do you think when you look at your page 7?
Copper is a stronger oxidizing agent.
Copper is the stronger oxidizing agent. So that means that this is going to be our strong reducing agent on this side. Okay? So when we look at the E cell, okay, the cell potential of the entire cell, the two beakers together combined by the cell bridge, we're going to look at the E cathode minus the anode. So what do we find the cathode to be? The cathode is going to be which one?
Oxidizing agent?
Cathode.
Yeah, the oxidizing agent.
Yeah.
Copper.
So it's going to be and this is going to be our anode. So what's the cell potential for copper?
Positive 0.34.
And what's the cell potential for the zinc reaction?
0.76. Negative.
Okay, so cathode. So the cell potential is
1.1 volts.
1.10 volts. another one. This is subtraction and addition. So SIGDIGS looks at the number of decimals that you have. So we have to make sure our answer has 2 values behind the period. Okay, it's not multiplication and division where you just look at the total number of numbers. When you're doing addition and subtraction, you look at the number behind the decimal. Okay.
And that's so many decimals. Like
So there's
that.
2 behind this one and there's 2 behind this one, so we need to make sure we have 2 behind this decimal. So what we're used to seeing is that we have 3 sig figs, but because it's multiplication and division, we need to make sure we have 2 behind the decimal. Calculate standard potential for the voltaic cell in which the following reaction occurs. This is the reaction. So what's the first thing that we have to do?
It's oxidizing, which is reduced.
Find which one's oxidizing, which one's reduced. This is a -1, this is a 0, this is a 0, and this is a -1. So going from -1 to a 0, what's happening? Are we gaining or losing electrons?
Losing.
And so this one here, we're going from a 0 to a -1, we must be then gaining electrons. So when we look back here, we have oxidation at the anode. So I minus is our anode. And Br2, this is our anode. This is our cathode. So what is the value for I2 and I minus?
0.54.
It's which cell?
0.54.
And what is it for bromine and bromide?
1.07.
They're both positive. 1.07.
Yeah.
Okay, so then what do we get for a value?
53. 3.53.
Okay. So it's going back to basics and it's figuring out which is the oxidizing agent, which is the reducing agent, so that we can figure out what's the cathode and what's the anode. There's no getting away. There's no shortcuts. Okay, use the standard cell described below to determine the standard reduction potential and the gallium half cell. This format of writing is always anode and cathode. Okay,
Every time, without fail.
without fail. That's the standard way of writing it.
Sweet.
You said yesterday there's something about we're not supposed to memorize it like left or right or something.
When you see the picture,
Oh, right.
but this format
Is
is
always like that.
standardized across every person that takes chemistry.
Okay.
Okay, but the pictures could be flipped. Don't think that this is always the anode and this is always the cathode. I have seen them flipped. Okay, but that was a good question. Okay, it tells us which one is the anode and which one is the cathode. We don't even have to do all the fancy oxidation numbers because we know the format for cell notation is this way. So it says determine the standard reduction potential of the gallium half cell. So we know this formula. Do a quick look through your book. Do you see gallium?
No.
No. Okay? So we have 0.90 volts equals E cathode. Or no, gallium. We have a cathode. Copper is
0.34.
0.34
Positive.
minus EA. So if I want to move that around to become positive, it's 0.34 minus 0.90 volts.
Meters.
Negative 0.56.
Pardon me?
Negative 0.56.
Negative 0.56. Okay? You what?
I'm showing Karen my haircut.
Oh, you,
I like it.
your hair's so long I didn't even notice.
It literally doesn't look like
5
it.
inches, 6 inches.
Holy moly. Okay,
And lowered it.
let's keep going.
And then it took like 20 minutes and 5 of it was Joey playing with my hair because she loved it.
Don't forget, that's for posterity's sake. Assume that the reduction half cell is changed to cadmium. So what is cadmium's cell potential? I'm just going to write it here because I can't reach way up there.
Yeah, it is. Negative 0.40.
Negative 0.40. That's what cadmium cell potential is, but we are setting it to the reference cell. The reference cell has to be 0. So how do I go from negative 0.4 to 0?
Add 0.4.
Add 0.40 volts. Okay? So, what would be the standard reduction potential for calcium then? What is calcium?
Negative 2.87.
Okay, so now we're going to use cadmium as the reference. Whoops. So what's the new cell potential for calcium?
So,
Everything in that book is related to hydrogen. But now we're saying we're going to relate
that
everything to
cadmium's the reference
cadmium.
Oh.
So cadmium becomes the new 0. How do we get it to become the new 0? We had to add plus 0.4 volts.
okay.
So now instead of everything being in relation to hydrogen, everything's now going to be in relation to cadmium.
That's done.
Well, there's probably a production, like a process for doing that. So what is the answer?
Negative 2.47.
Negative 2.47
47.
volts. So this would be the new calcium cell potential when it's in relation to cadmium. Okay?
Yeah.
What would be the standard reduction potential for silver? So what is it right now? In relation to hydrogen, it's what?
Positive 0.80.
So in relation to cadmium, it would be plus 0.80. We have to add 0.40. So we get 1.20 volts is the new standard reduction potential for silver when we're referencing it against cadmium. So it says, C, calculate the standard net cell potential for cadmium silver if the cadmium is the reference half cell. So we're looking at our calcium silver, sorry. So calcium and calcium 2 plus. And we're looking at silver and silver as a solid. That's what our two half reactions are, calcium and silver. Which one is which? When you look on your list, when we look at our values here,
Would silver be the oxidizing agent?
yeah. What made you say that?
It's higher up than calcium is on here.
Higher up than the calcium. So this is the anode. This is the cathode. So the new cell potential, when cadmium is the reference cell, is going to be silver. I'll just write this in. 1.20 minus negative 2.47. So the new cell potential, if cadmium is our reference, is
3.67.
Yeah.
Oops.
okay. And then it says calculate the standard net cell potential for the calcium silver using the hydrogen half cell as the reference.
Oh, oops.
So these don't change. They're still the reducing agent and the oxidizing agent, which means this is still the anode, this is still the cathode. But in relation to hydrogen, we need to go back to their original values, which is 0.80 volts minus negative 2.87. And we get what for a value?
3.67. Why do we do the same thing?
Because it's relative, right? It's relative. We took cadmium and we made it the new zero, so we had to change it accordingly. So when we do that, it makes it relative.
The same amount each side, still
Yeah,
values the same.
yeah. So you can make that note.
So if it asks you to calculate it for whatever, like you can just hydrogen?
You
like
could.
reference hydrogen, or do you have to like switch it around?
You could, but they're not going to ask you for, if they're asking you to change it based on something else being your reference cell, they're going to make sure that you know that you have to subtract or add that difference to get to zero. It won't be asking you to do the entire cell potential because you can just go and look at the two because you know that it's relative, right?